picture this real-world scenario from 2022. An ML team at a radiology AI company builds this chest X-ray classifier to detect pneumonia.
Okay, high stakes right out of the gate.
Oh, totally. And on their test set, it hits 94% accuracy. I mean, great precision, great recall. They ship it to a pilot hospital. Everyone's, popping champagne.
Right, a huge success.
Exactly. But 2 weeks later, a radiologist notices something absolutely terrifying. The model is marking every single scan from the night shift as negative.
Wait, like completely healthy?
Completely healthy, regardless of what the X-ray actually shows.
That is an absolute nightmare in a clinical setting.
Right. So the team completely panics. They rerun the automated test suite, and it still says 94% accuracy. All their checks pass.
Let me guess, 0 errors thrown.
Not a single one. It takes them 3 full days of just frantic digging to find the culprit. And it turned out the night shift scans were coming from a completely different imaging machine.
Ah, hardware differences.
Yeah, that specific machine saved files with a higher bit depth. So instead of pixel values from 0 to 255, they ranged from 0 to 4095.
Oh, wow. So the preprocessing pipeline just blindly divided by 255, assuming standard images.
That's the trap. So the night shift scans were scaled to values between like 0 and 16 instead of 0 and 1.
And the model has never seen that range.
Exactly. So the neural network inputs just completely misfire. The model had no idea what it was looking at, so it defaulted to the dominant class negative.
Just confident, silent, and entirely wrong predictions.
Yeah. The cost was 2 weeks of dangerous clinical advice, lost trust, and a 6-week delay. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
That X-ray story just perfectly frames our mission for today's deep dive.
Yeah.
Because it highlights the fundamental difference between traditional software and ML engineering.
Right, the silent failure.
Exactly. In software engineering, a bug causes a crash, right? You get a stack trace, a glaring red error message. But in ML engineering, bugs cause those confident, silent failures. The system just won't tell you it's broken.
It'll happily serve garbage to your users all day long.
All day. So today, as mentors, we're going to teach you how to detect what we call incorrect reality and debug ML systems at a FN-ready level.
I love that. But to fix those silent failures, you obviously can't use traditional debugging. You can't just hunt for a syntax error.
No, you have to completely rewire how you think.
Oh.
A junior engineer looks at a failing model and asks, where's the bug? And that just leads to endlessly reading code.
Which is exhausting.
It is. A senior engineer, though, asks, which assumption about this system is false?
Ah, that's a big shift.
Yeah, it leads you to verify reality. We call this systematic skepticism. And there are 5 core principles here. Reduce to the simplest form, use distributions because samples conceal bugs, make every assumption explicit, isolate before you fix, and verify every fix with a full pipeline rerun.
Okay, systematic skepticism makes sense. But practically speaking, when you have a massive neural network, millions of parameters acting up, looking for a false assumption feels like looking for a ghost.
Sure, it can feel overwhelming.
Right. So what is the absolute first keystroke you make?
Well, the very first move is applying the baseline rule. You never, ever start by debugging the complex model.
Really? You don't even look at it?
Nope. You temporarily replace it with the simplest possible model. Like, pull a basic logistic regression right out of scikit-learn, train it on the exact same data pipeline, and just see what happens.
Okay, but wait. If my massive neural network is failing, replacing it with a logistic regression feels like taking a Ferrari to the mechanic and having them test the engine by swapping in a lawnmower motor.
Exactly. But if the baseline works, then your data is fine, and your complex model is the problem. That single move eliminates 50% of the search space instantly.
Wow. Okay, so it's a massive time saver.
Huge. Once you know whether the bug is in the data or the model, you need a systematic framework to hunt it down.
Right, which brings us to the 6-step framework. So step 1, reproduce.
Yes, you have to fix all sources of randomness. Lock your random seeds in NumPy, PyTorch, whatever, and shrink the scale.
Like just run one batch or one epoch?
Exactly.
Yeah.
Because an unreproducible bug is an invisible bug.
Yeah, that makes sense. Once it's reproducible, step 2 is tracing the data flow. You check shakes, numerical values, and data types at every single transition.
Right, don't assume anything.
Which leads to step 3, and I think this is crucial. Stats over samples. Looking at 2 rows of raw data to find a bug is like tasting 1 drop of ocean water to see if the whole ocean is polluted.
That ocean analogy is spot on. You absolutely must look at the distribution stats, the mean, standard deviation, min, max, and nan counts.
Because samples will just lie to you, right?
Completely. Think about a medical data set tracking blood glucose. The normal mean should be around 100 milligrams per deciliter.
Right.
Let's say unit conversion error bumps that mean up to like 1,800,000.
Which is absurd.
Right, but if you just pull 2 random rows to check, it might just look like 2 wild outliers.
Yeah, you just think, oh, a couple of bad records.
Exactly. But the statistical mean reveals the catastrophic failure instantly. Distributions reveal bugs, samples conceal them.
Okay, so step 4 is validating those assumptions. And my favorite way to do this is making assumptions explicit using Python assert statements.
Yeah, those are lifesavers.
I always explain assert like setting up laser tripwires in your
Yeah.
pipeline. If you expect 32 features, you literally write assert x shape 1 equals 32.
And if it fails, the script just stops exactly where the assumption broke.
Exactly. No silent failures.
Okay.
Then step 5, isolate. Test loading, pre-processing, and the model forward pass in complete isolation.
Right, break it into chunks.
And finally, step 6, verify. After you make a fix, you rerun the entire pipeline from scratch, including all your edge cases.
Yes, you have to prove the fix actually worked. Let's ground this with a couple of real-world production nightmares.
Oh, I love these.
These are cases that produced 0 error logs. Case 1, the case-sensitive extension bug. An ML team is training a tumor classifier, and in validation, it never predicts malignant.
Never. Not even once.
Not once. Why? Well, it turns out the malignant slides came from a different hospital system and ended in uppercase JPG.
Oh, no. And the data loader.
Look for lowercase.jpg. And Linux treats those as completely different strings.
So it just silently skipped all the malignant
Heck,
data.
all of it. The model just learned to predict 100% healthy.
That is brutal. But the fix is so easy, right? Just use useloader.
Sure, but to prevent it entirely, you just check the class distribution using counter before you even start training.
Right. Step 3, stats over samples. What's the second case?
Case 2 is pre-processing consistency. So a fraud model absolutely crushes it in offline evaluation, but misses massive fraud in live production.
Okay, what happened there?
The training data was normalized using the training set's mean and standard deviation, but the serving pipeline, written by a totally different engineer, normalized using a default mean of 0 and SWAIT of 1.
Wait, hold on. Shouldn't the production pipeline just, dynamically calculate the mean of the live data coming in?
Absolutely not. Never do that.
Really? Why?
Because that changes the baseline constantly.
Yeah.
Your model is receiving a numerical language it didn't speak during training. You must fit the preprocessor on the training data, save it as a versioned artifact.
Like a pickle file.
Exactly. And load that exact identical artifact in serving. You check this by comparing the serving input mean to the training input mean.
Wow. Okay. That is a massive trap. So to catch these things, print statements are a good start, but they won't cut it for industry-grade systems. What tools should we actually use?
Well, the Python debugger is huge, using breakpoint to literally pause time and inspect variables interactively.
Oh, that's so much better than 100 print statements.
Way better. Then there's visual debugging, plotting histograms of layer weights. Healthy weights are clustered near 0. If they're exploding or all zeros, your system is broken.
Which brings up gradient inspection. We hear about vanishing and exploding gradients, but mechanically, what does that mean?
If gradients are near 0 vanishing, the model receives no signal to update. It never learns. If they're huge exploding, the updates are so violent, the math destabilizes.
And what if they're NaN?
That's math instability, like dividing by 0.
Speaking of traps, I want to walk you through a micro exercise about a classic code trap. Silent data leakage.
Oh, this is a classic.
Right, so imagine you have a data set. You apply standard scalar.fit, and then you split the data into training and validation sets. You train, and your accuracy looks amazing. No errors at all.
But mathematically, it's a total disaster.
Exactly. Why is that such a disaster?
Because by fitting the scalar on the whole data set, the mathematical mean of the validation data has silently leaked into the training process.
So the model has basically subtly seen the future.
Right, it's cheating. The fix is to fit the scalar only on xtrain, and then transform both xtrain and xval.
That strict chronological isolation is so important. So how do we translate all these mental models into, say, passing a FANG level senior ML interview?
Let's run some rapid fire scenarios.
Okay, question one. You build a model, it works locally, but it fails in prod. Go.
I'd verify environment parity and order. First, data consistency, compare the input stats. Second, environment differences like Python versions or CPU versus GPU precision.
Right.
Third, data ingestion time zones or encodings. The key phrase to use in the interview is same code does not mean same environment, and same environment does not mean same data.
Oh, I'm writing that down. That is gold. Okay, question two. Works in offline evaluation, fails in prod.
I'm looking for distribution shift, data leakage like future info slipping in. Also preprocessing inconsistency or flawed evil setups, like random shuffling on time series data.
Okay, question three. NAND loss after a few batches. NAND loss is like the engine just melting down. What causes that?
It's pure numerical instability. First, drop the learning rate to stop aggressive overflow, then check for log 0 in the cross-entropy loss
How do you fix that?
by adding a tiny epsilon value to the probabilities. Then inspect gradients for NANDs and assert no NANDs in the input batch.
Nice. Question four. Debugging data leakage.
Ensure chronological splits. No time travel allowed. Audit your features. Could this data even exist at prediction time? And ensure scalars are fitted only on training data.
Okay, last one. Debugging a massive system with no idea where to start.
Structured reduction. Start with the baseline model, apply the 6-step framework, and state clearly to the interviewer, debugging ML systems is applied hypothesis testing, not code archaeology.
That is such a mic drop answer.
It really works.
All right, as we wrap up, let's do a quick summary checklist, the ship or don't ship list.
Let's hear it.
You need your baseline established, reproducibility fixed, class distribution verified, and stats checked at every stage.
Right.
You need assumptions made explicit with asserts, isolation achieved, preprocessing consistency confirmed, and finally, the full pipeline rerun.
Perfect checklist.
Now that you know how to diagnose when systems fail, we need to talk about building systems that are operable, reproducible, and usable by your whole team. In the next video, APML ZO7 will cover CLI tools and automation, turning your ML code into professional systems.
And I just want to leave you with a final thought to ponder. Today we talked heavily about systems that fail silently because of data or math, right?
Yeah, all the internal stuff.
Right, but what happens when the system functions perfectly? The math is completely sound, but the world itself changes overnight.
Oh, wow, like consumer behavior shifting.
Exactly. How long would your perfectly debugged model confidently predict yesterday's reality before you even noticed?
That is a genuinely terrifying thought. It just goes to show you always have to be verifying reality. Thanks for joining us on this deep dive. Keep questioning your assumptions, and we'll catch you in the next one.